Hello everyone, welcome to my thesis defense. The topic of my master thesis is Enabling Human-in-the-Loop Interpretability Methods of Machine Learning Models, the case of bird species identification. With this 30-minute presentation, I will walk you through the academic background, design activities, and the final outcomes of this project. Okay, let's start with the academic background. Nowadays, AI, or artificial intelligence, has been put use to a broad range of applications in our daily life, from the field of medicine, education, to robotics, biology, etc. Today, we're gonna talk about how AI is used in species identification with the image classification techniques. As you may already know, the AI are usually made possible with machine learning. Machine learning refers to the methods that enable computers to learn from data and make predictions. Generally speaking, a machine learning pipeline consists of 3 steps. First, data collection. We need to get a data set at this step with the outcomes that we want to predict, along with the paired information used to predict the outcome. The more data, the better. Second, training the model. Here we enter the training data into a machine learning algorithm to train the model. Third, after a model has been trained, we use the model with new data input. A powerful tool as AI might be, it still faces some challenges. The biggest one being its opaqueness even to its creator, due to the complexity in its mechanism. We use the word black box in machine learning to describe models that cannot be understood by looking at their parameters, such as the neural network, which consists of a large number of interacting and nonlinear parts and is very often used in our context of species identification. Now, suppose you are a bird enthusiast, and one day during a trip you saw a glorious bird that you've never seen before. You can take a photo of it and the bird ID app will tell you its guess. But someone who are not so knowledgeable in birds, you might also want to know why the app thought that bird was that bird. Not only would the birders like to know the rationale behind the algorithms in order to trust them or to learn from them, the developers will also be interested in it in order to debug the models or to improve them. Looking into the rationale of machine learning algorithms is what the research field of explainable artificial intelligence, or XAI, concerns. The traditional AI can make decisions, but it doesn't let you know why it makes such decisions. The XAI is the ability of algorithms to explain their reasoning and characterize the strengths and weaknesses of their decision-making process. And the word explainability or interpretability are used to describe the degree to which a human can understand the machine learning models. Different types of problems will need different strategies for explaining. For the image classification tasks based on neural networks, like in our case, saliency maps, i.e. the highlight on the most important pixels for classification of a given image, can be used to reveal how each pixel contributes to a particular prediction. While the saliency maps are not usually understandable to the end users by itself, we adopt the seeker framework, meaning the semantic concept extraction and analysis framework, to produce semantically understandable explanations to the end users. Here's how the seeker works specifically. Firstly, using the normal image classification model and an image dataset, the framework first generates saliency maps on the original photos. Then, it recruits human labels to draw bounding boxes around the salient areas and make annotations on those areas. Finally, the developers extract general rules for different classes in the model from the annotations to build an explainable machine learning model. This project adopted the seeker as the theoretical basis of our study, and the developer of seeker has provided me with technical support along the process, including the dataset of bird photos, classification models, and photos with saliency maps and bounding boxes, which will be used in the prototype test. The focus of our study will be on how to design the annotation process to engage the end users and to effectively collect useful annotations. The other focus is to study how to communicate the explanation to the end users. To wrap up, as a human-in-the-loop method, we need annotation input from human to build an explainable model. We hope the end users can make the annotations for us, but we need good reasons to motivate them to do so, and we assume that learning will be that motivation. In this project, we construct a framework that benefits both the end users and the developers in the development of explainable models. We evaluated the idea of a game-like bird ID learning platform, which can collect annotations from the end users on the basis of Zika framework. And we explored the opportunities of applying explainable AI in the education of bird ID knowledge. The project aim was twofold. One lies along with the developers' needs to collect annotations, to explore how the end users can contribute to the development of machine learning interpretability. The other one lies along with the end users' need to develop a bird species identification platform that engages them and enables them to learn to identify birds. With the project aims framed, we raised the following research questions. First, can the end users learn about bird species identification with machine learning explanations and the annotation tasks? Second, how can we engage the end users in contributing their annotations with the design of a game-like bird species learning product? And third, are the end users able to make annotations needed by the developers through a game-like process? The research questions were corresponding with the two project aims. The project started with user research to understand the end users, with approaches like interviews and online surveys, followed by 2 rounds of ideation through rapid prototyping, one on the explanation, the other one on the annotation. Then we wrap it up with interfaces tests and final discussion. Firstly, we need to understand what our end users want. The research question was, what are the opportunities and challenges of bird ID apps in teaching people to learn about birds? And we conducted semi-structured interviews among 3 participants, mini-surveys with 10 replies, and a formal online surveys with 49 replies. Through the interviews and mini-surveys with both experienced or inexperienced birders, we found that though the bird books are considered the most reliable and comprehensive learning materials, bird ID apps are super valuable starting tools for beginners, and they are often used in combination with other tools. Like shown in this diagram, the learning not only happens in the birding and identification itself, but also in the process of doing preparation and follow-up. Among all the knowledge that the birders would love to know, including the bird's behaviors, habitats, etc., not all of them are suitable to be taught with explainable AI. For our project, with the data enabled by photo classification models, we want to make it clear that we aimed only at this purple bit of the Venn diagram shown here, which means teaching birders to identify birds by their appearance. Then, in the online service, we got to learn the behaviors and interests of different layers of birders, and found out that compared to birders of all the other levels, entrance and intermediate level birders are most likely to adopt bird ID apps as their main learning tools for learning bird knowledge. Based on the results of the survey, we defined 4 different levels of birders, which are the complete novice, who have zero bird knowledge before but would like to learn some out of curiosity, the beginners, who don't have much bird knowledge but decide to develop birding as a hobby, and the intermediates, who have beyond average level of bird knowledge and want to learn more in-depth knowledge of ornithology, and the advanced or expert birders, who are familiar with most regular birds around their places and know a lot about bird knowledge such as behaviors, migration of birds, etc. According to their different needs, we chose complete novice and beginners as our main target users because they are most likely to adopt bird ID apps as their main learning tools, and what we're designing for suits their learning goals. Intermediate birders, meanwhile, were chosen as our potential users. Okay, we've figured out about our end users, and now what do explainable machine learning models mean to them? The research question of this phase was, what are the design opportunities for explainable AI models in the birding community? To study this, we built 3 mockups representing 3 different ways of providing explanations. 6 participants have taken part in the user tests, whose expertise ranging from complete novice to advanced level. During the user test, a starting page containing normal input and prediction function was shown to the users at the beginning, leading to 3 add-on features. The first add-on feature was feature description, highlighting all the important features in the bird's appearance in a combination of visuals and text. The second feature was result comparison, showing the contrast between 2 or more similar species. And the third one was showing samples, which provided abundant sample pictures in the dataset for the users to check. In the evaluation session, the participants were asked how the properties in each prototype helped them in learning or in reaching their other goals. The highlights on the photos, according to the participants, taught them where to focus in order to identify the birds, while the comparison of prediction results helped them distinguishing different species. And some new ideas on the information communication were also generated during this session. These ideas include showing more detailed characteristics of the birds, such as feather pattern and bill shapes, as they think this could better help them identify the birds. And showing sample pictures for different ages, genders, or molting stages in the same species to provide more information in their appearance. To conclude, the explanation on bird species identification results can help the ancient bird hobbyists in knowing where to focus when recognizing birds, and in knowing the contrast between 2 similar birds. And we knew from the ideas they raised that the users want to learn about the subtle differences that characterize different species, and about the different appearances of different gender ages within same species, which were currently missing in the explanation prototypes. Then we're going to explore how our target users are able to help the developers. The research question was, to what extent are the end users able to make annotations correctly on the photos pre-processed by the developers? To study this question, we set up a scientific experiment with a quick mock-up of the annotation process. 16 participants took part in the experiment. In order to simulate how the annotation happened in real life, we used a real classification model of 10 species and a bird photo dataset. With every photo in the dataset, there was a saliency map on that bird photo and an image with bounding boxes drawn by the developer on the saliency map. There were 2 identification tasks in the testings. one at the start and one at the end, to see how well the participants could tell the two target birds apart. The participants were asked to choose from the two options for each bird on the 10 provided photos in the identification task. We recorded the correctness and asked how confident they felt during the identification task. Between the two identification tasks, there was a description task, i.e. the annotation task, where the participants were asked to describe body parts and colors on the bird photos using the provided vocabulary. We calculated the correctness of the annotations by counting how many right descriptions they made out of the total number of queries. The descriptions made by the researcher and the model developers were used as baseline. Here's how the experiment is structured. After a brief introduction session that introduces the participants to the characteristics of the two target birds, they were asked to complete an identification task with 10 bird photos. And then they were asked to do the description task, where 4 bird photos are presented to them for annotation. Finally, the experiment ended by another identification task with another 10 photos. We had 4 hypotheses framed around the research questions. 1A, the participants can make annotations with high accuracy on the testing bird photos with bounding boxes. 1B, the participants can make correct annotations even on the photos that are difficult for the model to classify. These 2 hypotheses can be verified with the correctness of annotation made by the participants. And we found that correctness was beyond 93%, even that on the difficult photos were beyond 92%. And the most popular descriptions picked was 100 correct in our test, which meant the hypothesis 1A and 1B was proved. And we also assumed that the participant can do better or be more confident in telling birds apart after completing the annotation. These 2 can be verified by comparing the participants' confidence and correctness level of the pre- and post-identification test. We carried out t-tests to these 2 values, but we didn't notice any significant difference between the values of pre-test and that of post-test, which meant the hypotheses weren't confirmed. To conclude, it was found out at this stage that participants were able to make annotations with a correctness more than 93%. And if the developers use the mostly picked descriptions from the participants, it will be always correct. But participants' confidence level and correctness in identification didn't improve significantly after annotation tests, so it didn't have strong evidence to prove that the annotation helps in the learning of identification. Finally, we put together the explanation and annotation parts to set up the interfaces test. The research question of this phase was how to design an interface that people would like to use for learning and making annotations. We carried out interfaces tests with a prototype that integrated both the explanation and annotation parts into a gamified process. And we mainly cared about how engaging the prototypes was to the end users, as well as its usability. We used the photos from the same dataset as what we used in last stage and edited them to be suitable for the prototype. For the reference diagram, we picked a topography diagram as reference for body parts. For color, build shape, and patterns, we used the diagrams provided by wordbird.com website as the reference vocabulary for participants to choose from. Here's an overview of the complete prototype. The learning session starts with a guideline on how to complete different tasks. Then the participants will be introduced to the main characteristics of the target birds, shown with bounding boxes and textual description. After, the participants will be presented with classification tasks and annotation tasks, alternatively as the main learning activities. The prototype was evaluated among 3 participants from complete novice or beginner levels. After trying out the prototype, they were asked to fill in a questionnaire, mainly consisting of 2 parts: the system usability scale with 10 questions and the subjective feedback session using the Primo toolkit. The prototype gained an average of 87.5 out of 100 in the system usability scale, which means best imaginable in usability. When asked their subjective feeling during using the products, the description of joy, confidence, fulfilled, motivation, and attraction has been chosen by 2 participants out of 3. Besides, we received the following positive feedback from our participants. They liked that the repetition of the annotation tasks helped them solidify the knowledge, and the tasks helped bringing attention to details. They also admired that the knowledge provided in the prototype was getting deeper, which was helpful for learning. Overall, the interaction design for the annotation task was easy to understand by the participants with a good score in usability scale, and the process was seen fun and engaging to the users. Participants also thought positively about learning to identify birds with such a process. Now, taking all the pieces together, let's see what we got. We have defined our target users to be complete novice, beginner, and intermediate birders who are interested in learning bird knowledge. Then, for our first main research question, can the end user learn about bird species identification with machine learning explanation and the annotation tasks? We have found out that the explanations are able to help them know better what characterizes the target birds, and the annotation tasks help them get more familiar with the features of the birds, both of which help them in learning bird identification. The second research question: how can we engage the end users in contributing their annotations with the design of a game-like bird identification learning product? During our interfaces test, we found that the participants agreed that using the product was an enjoyable and interesting experience for them, and the belief that they can learn about bird identification with this process has also made the product sound more attractive to them. And our third research question: are the end users able to make annotations needed by the developers through a game-like process? And we proved in our annotation test that the end users are able to make annotations with a high accuracy of 93% average. And we have these implications on design. For annotation collection, we advise the developers to choose the most popular descriptions, which were always correct in our experiments. Practices are needed for the end users in advance to ensure high accuracy in annotation. For designing user-friendly interactions and interfaces, we suggest to provide clear enough guidance with examples, which will largely influence the completion of the given tasks. The order of different tasks also need to be carefully designed for the best learning outcome. While our study proved the feasibility of such an approach, we realized that more work has to be done in terms of incentivizing people to do it. Additional particular user modeling, as well as more work or gamification design is required. For example, by carefully developing the leveling system, giving tasks of varying difficulty to people at various levels. In the future, we can expand the range of information to explain from the visual characteristics of the birds to location, habitats, behaviors information, and even the cost of the birds, as is wanted by the birders. For example, when the users are provided with the calls of birds, they can annotate them with the provided vocabulary so that they can learn to recognize the birds with their calls and to help our model to explain the call information. That is to say, the framework we investigated in this study has the potential to be used to a broader range of applications while machine learning classification models are used, as indicated by the above conceptualization. This was all of my presentation. Thank you for listening, and I'm happy to answer any questions.